The reason we care about the integration techniques that we discussed in the first part of the course is that they are applicable to actual practical problems. For example, integration techniques can be used to solve differential equations, and differential equations are a very convenient way to describe nature's laws. So for example, if we have a body of mass m attached to a spring with stiffness k, then by Hooke's law, the force that acts on this body for small deformations of the spring, for elastic deformations of the spring, is given by minus k times x, as you know well from courses of physics. So here x is the deformation of the spring, and the minus sign accounts for the fact that if we deform spring to the right, say we extend the spring away from the wall, then well, that is in the positive direction of the x-axis, then the spring pulls back the body towards the wall in the negative direction of the axis, and hence the minus sign. So here x is deformation. Now, what does it mean? What does it tell us about x? Well, we know by the second Newton's law that force here is equal to mass of this body times its acceleration. And again, acceleration is the second derivative of the coordinate. So what this tells us is that m times the second derivative of x equals minus k times x. And so here we obtain the law that describes the motion of such a body attached to a spring. And so we start with a system and we obtain description of its evolution as a differential equation. So as a result, we want to know how to solve differential equations. We will not discuss differential equations of this form. This is an example of second order differential equations. We'll only discuss first order differential equations, specifically the ones in which variables can be separated. So let us now discuss what these separable differential equations are and why we're interested in them. So first, some general remarks about differential equations. What do we mean by differential equation? Well, in general, we want to think about the, say, now we change gears slightly. So now we say that y is an independent variable and x is a dependent variable, whereas here we had x as our dependent variable and it depended on time. Now in here we'll have y as a function of x. So we want to talk about separable differential equations. So as stated in the title. Now for such pair of variables, we want to think about the plane, the xy plane. And in this xy plane, we think of there being a direction, a vector of direction attached to every point x, y. Okay? And this vector that exists at every point in the plane will tell us the tangent to the curve, the y of x curve that passes through this plane. So in other words, what a differential equation is, it prescribes the slope of curves at every point in this plane as a function of location in the plane. In other words, we want to prescribe the derivative y of x as a function of both x and y. Now this is the general form of a differential equation. So this is general differential of the first order of one variable. So this is the so-called ordinary differential equation. Now we say that such an equation is separable and this name gives rise to the name of the type of equations we're talking about here. If the function big F of xy can be written as a product of two functions that depend only on x and only on y respectively, so that we have g of x times f of y and dy over dx equals g of x times f of y. So now, assuming that f of y is non-zero, we want to think of this as g of x divided by h of y. In other words, we are setting h of y to be 1 over f of y. And so for such an h of y, we can separate the variables in the following way. And we'll get dy, let's put it this way. We have h of y dy equals g of x dx. And this equality between differentials can be integrated. So that gives integral of h of y dy equals integral of g of x dx. Now solve this. So the claim is if we solve this for y as a function of x, we get solution to our original equation. So we will then find a function y of x such that if we plug it into the original equation, this is the original equation here. So once we plug in that y of x into the original equation, we will get an identity. So this is precisely the point. The goal in solving a differential equation is to find a function that satisfies it, such that if we plug in that function into the equation becomes an identity, true for all the values of x in the domain of that function. And so to verify this, to verify that this the solution of this equation is indeed the solution to the original equation that I highlighted here, we want to differentiate both sides of this identity. So what we want to do is see that y of x solving, let's see, from this equation solves the original differential equation. And again, to solve a differential equation means to make it identically true for the values of x from the domain of your function. Differentiate equation star. And so what that means, we want to differentiate with respect to x, this here, and in the right hand side we'll be differentiating this antiderivative. Now differentiating with respect to x is the same as differentiating with respect to y. Okay, so what we want to do is basically apply a chain rule, which says that in order to differentiate with respect to x, we may just as well differentiate with respect to y, and then multiply by the derivative dy over dx. So this is effectively an application of the chain rule. And in the right-hand side, well, we can just go ahead and evaluate the derivative, because differentiating the antiderivative returns us back to the function. And then here, if we differentiate this antiderivative, we get back to hy. And so we get that h of y times dy over dx equals g of x. And this is precisely the original function, the original relation that we started with. So here we have dy over dx equals gx over hy, and this is precisely what we get here as well. So the conclusion here is, if we start with an equation, dy over dx equals g of x times f of y, and we want to find a function y of x such that we plug it into this equation, we get an identity, then this function can be found as follows. We separate the variables for the equation to get to this form, then we integrate both sides, we get, again, a new equation, a new equality between two functions, and solve this equality for y is a function of x. Once we do that, we will obtain the solution to the original differential equation. So this is how we're going to solve separable differential equations using this method. Now, we will illustrate it in the following